Hello, and welcome to the second day of Unit 2. So this is all about transforming or altering data, and then what those transformations do to the various statistics that we calculate from that data. All right, this is also going to be really important when we start looking at the normal distribution and something called the standard normal distribution, which relies on some of these transformation properties. All right, so that's why we're going over this today. So the question at the top there is, what happens when we change each data entry by either multiplying by a constant or adding or subtracting a constant from each entry? So here we have a distribution. All right, these are just made up test scores. All right. So sometimes teachers curve tests, right? And one way that happens is taking the highest score, setting it to 100, and then whatever you added to that score, you add to every other single score. So let's pretend that we were going to add 9 to every single one of these test scores. So a 91 would become 100, an 87 would become a 96, and so on and so forth. What we're going to do is we're going to start by calculating one variable stats for the normal data before the curve. So there it is right there. I've typed it in already. I'm going to go to stat calc, one variable stats. It's in L1. And I'm going to run that. And I'm going to use this to fill in this part down here. All right, so the minimum score was a 51. The quartile 1 was 74.5. The median was 78. Quartile 3 was 84. The max, I don't really need my calculator to see the max, it was a 91. X bar was 78.08. 78.08. The population standard deviation, because if this is every student in the class, all right, that might be our population for the test. So we can use population here. 9.096. I'm going to round that up to 9.10. And then the IQR, we remember, is Q3 minus Q1. So 84 minus 74.5, which is 9.5. All right. So what we're going to do now is we're going to take all of those scores and we're going to add 9 to them. So if you want to test a transformation in the calculator, the easy way to do that is go back to your stat edit. I have the original data here in L1. If I scroll over to L2 and then go up top here, down at the bottom, I have this L2 equals. And what I can do is I can type in L1, which is the second key, and then the 1 key. That'll give me L1. And I can say plus 9. And that will go through and add 9 to everything for me. So instead of me having to retype everything in, I can just say L1 plus 9. And it will go through and transform that data. And then if I want the calculations, I can go to stat calc, one variable stats, and then just tell it that I want to run it on L2 instead of L1. And what we see here is, all right, let's fill these in one by one. The min went up by 9. So it's now 60, which makes sense because the lowest grade got 9 more points. Q1 is now 83.5. The median is now 87. Q3 is now 93. The maximum is 100. The average has gone up to 87.08. The standard deviation is still 9.096. So I'm again going to write that as 9.10. And the IQR is now 93 minus 83.5, which is still 9.5. So we talked about this a little bit on the day that we did the standard deviation activity. But what you should notice is that our measures of center, mean and median, have both gone up by the same amount we added to each score, which sort of intuitively makes sense. If you give 9 extra points to everybody, the average is going to go up by 9 points. However, our measures of spread have stayed exactly the same. All right, so down here in the what happened, we're going to say the mean went up by 9. The median went up by 9. And the spread, so our standard deviation, stayed the same. And our IQR also stayed the same. All right. So the general rule that we can take from this, that we can apply anytime we're doing a transformation, is when we're talking about measures of center, if you add or subtract, so it doesn't matter which, a constant to every value in a distribution, add or subtract again the same value to the mean and median. All right, so that's our general rule, that if we add or subtract a constant to every single value in our distribution, we get to add or subtract that same value from the mean and median. All right, and then over here, for our measures of spread, the general rule is, starts the same way. If you add, subtract a constant to every value in a distribution, and again, the every is important because if it wasn't everyone, this wouldn't actually be true. The measures of spread and the 3 measures of spread that we have right now are range, IQR, and standard deviation do not change. All right. So visually, kind of what's happening is if you have a curve, when you add or subtract a constant, all you're doing is shifting that curve in one direction or another. You might be shifting it to the right, you might be shifting it to the left. So if this is your center, the center moves, but how spread out things are has not changed. All right, it's still equally spread out, which is why the measures of spread don't change, but the measures of center do change. All right. So moving on. What about when we multiply by a constant? So now we're not talking about adding or subtracting a constant. We're talking about multiplying or dividing by a constant. All right. So if you were in class, I would now be collecting all of your heights in inches. All right. So I'd be like, hey, what's your height in inches? What's your height in inches? What's your height in inches? And we would gather all of that data. Since this is a video, I can't actually gather that data. Instead, what I did is I just went and randomly typed in a bunch of heights, again, in inches inside of L3 here. All right, so I've got 10 different people in here. And this is going to just be what we're going to use so that we can go through and talk about these notes. So again, I'm just going to go to stat calc, one variable stats. This time I'm going to switch to L3 because in mine it's in L3. And I'm going to get some values here. All right, so the mean, I'll just fill it in while I'm here, is 61.8. The standard deviation, again, I'm just going to pretend that this was the population. It was everybody that we were concerned with. So I'll use the full 2.56. I'll pretend it was our entire class. So I'm going to use the 2.56, but I could have also used the 2.70 from the sample, but I'm going to just stick with population here. IQR, I've got to go down and do this first. So the min was 58 inches. Quartile 1 was 59 inches. The median was 61.5 inches. Q3 was 64 inches. And the max was 66 inches. All right. Q3 minus Q1 is 5. So my IQR would be 5 here. All right. So again, that's just made up data. There's nothing special about it. It's just the data that I randomly typed into my calculator. All right, now what we're going to do is we're going to multiply each of those values by 2.5 because roughly if you multiply inches by 2.5, that converts it to centimeters. So again, instead of having to retype in all of those values, I can go to stat edit. I'm going to go over here to L4. I scroll up so the cursor is actually highlighting the L4. And then I can do L3, which is second and then the 3 key, times 2.5. Hit enter, and it will do all of those for me without me having to go through and do them one after another, which would have been annoying. All right, so once they're in there, I can go to stat calc. I can go to one variable stats. I can switch it over to L4. I can hit calculate, and this will give me my new results. So my new mean is 154.5. My new standard deviation, and again, I'm going to use the population, is 6.40. All right, I can't do IQR yet. I got to get all my other stuff. My new min is 145. My new Q1 is 147.5. My new median is 153.75. My new Q3 is 160. And then my new max is 165. All right. Which would then make my IQR 147.5. 147.5 and 160 would be 12 and a half. So 12.5. All right. So what happened this time? Now, it might not be immediately obvious, depending on how your mental multiplication goes, but 58 and 145 are connected. 58 times 2.5 is 145. So that same number that we multiplied all the observations by is what we're doing with our min here. Same thing with our Q1, same thing with our median, same thing with our Q3, same thing with our max. These numbers are all their original values times 2.5 down here. And the same is true for our average here. All right, if I do 61.8 times 2.5, I get the 154.5 that you're seeing down there. So what happened? All right, the mean was multiplied by 2.5, and the median was also multiplied by 2.5. Now, let's head over here to our measures of spread. Again, it might not immediately be obvious, but if we do 2.56 times 2.5, we get 6.4, which is what we have down here. If we do 5 times 2.5, we get 12.5, which is what we have right here. So, unlike on the front page, where the standard deviation stayed the same and the IQR stayed the same, here we're finding that the standard deviation was multiplied by 2.5, and we're also finding that the IQR was multiplied by 2.5. All right. So, based on what we just observed, here's the general rule that we're going to apply. So, if you multiply / divide every value, let's use the same language. If you multiply / divide a constant to every value in a distribution, then you are going to multiply / divide the mean and median by the same constant. Okay. Which again is probably intuitive. If you double everybody's score, you're going to expect the average to be doubled, right? And that's what happens. What's different here is that this same rule applies over here in spread. So you could almost just write samesies, but that's probably not very academic to just write samesies. And since I'm a teacher and I'm putting this up on the internet, I'm going to write out the whole thing. But, if you just wrote samesies, it's pretty much the same thing. If you multiply / divide a constant to every value in a distribution, multiply / divide the measures of spread which again, just to be consistent, I'm going to list them: range, IQR, standard deviation, by the same constant. All right. So visually, sort of what's happening here is before, all we were doing was shifting the curve left or right. All right. When we multiply, we're actually changing the shape of the curve, and we may make it like more or less spread out. The other example that I've done before, and I'll just show it again here, is imagine that you have some test grades. And we say, all right, not even test grades. I'm just going to use simple numbers here to make it even easier. So we've got 3, 4, 6, and 7. All right. Those would all average out to be 5. All right, 7 plus 6 is 13, plus 4 is 17, plus 3 is 20. 20 divided by 4 is 5. Now, if I double all of these, 14, 12, 8, and 6, the mean is going to double. All right, 14 plus 12 is 26, plus 8 is 34, plus 6 is 40. 4 divided by 4 is 40 divided by 4 is 10. So we've gone from 5 to 10. But also notice that things are now more spread out. All right, here the range was 4. Here the range is 8. We've talked that standard deviation is the average distance from the mean. All right, here we had things that were 1 and 2 away from the mean, 1 and 2 away from the mean. Here, if the mean is 10, now we have things that are 2 and 4 away from the mean. We have things that are 2 and 4 away from the mean, so that's going to have to go up. All right, when we double it, we're not only doubling the values, we're doubling the distance between the values, which is why it's more spread out, which is why these values also increase. Whereas when we're adding and subtracting a constant, we're just shifting it left or right, which is why the spread does not change. And that's the main thing that you need to take from today. That's the main thing that you have to keep in your head, is that adding and subtracting only affects the center. Multiplying and dividing affects both the center and the spread. All right, so where do you stand, literally? All right, so again, if you were in class, you would be calculating your individual percentile, and you would be calculating your individual z-score based off what we just did. All right, so instead, we'll just use my value. All right, so I am a gigantic 5'6", and if we go back to our data, we can see that 5'6", which is 66 inches. Oh, that's actually the tallest person in our group. Wow, I guess I am really tall. Huh, who knew? Sure, it's just a coincidence. So we know that a percentile is the percent below our observation. So my observation was 66 inches. That was actually the tallest person in this group. There were 10 people in the group, which means that 9 out of 10 were less than me, or 0.9, or 90%, or we could write that as the 90th percentile. All right. Now, where does it fall in relation to the mean, above or below? How far above or below? Basically, what is the z-score for my height? So again, remember z is the observation minus the mean divided by the standard deviation. So my observation again was that super tall 66 inches. The mean from the previous page was 61.8 inches, and the standard deviation was 2.56 inches. All right, so if we work that out, 66 minus 61.8 divided by 2.56, we end up with a z-score of 1.64. And again, that's standard deviations above the mean. Positive means you're above the mean. Negative means you're below the mean. All right, so the thought questions then are, how would converting your height to centimeters change your percentile? All right, so if the percentile is measuring the percent of observations below, if I switch to centimeters, is that going to change how many people are below me? No, right? Like, we're still the same height. Measuring us in centimeters versus inches doesn't change how tall we are. So the percentile would not change. Right? And the reason there is, changing units doesn't change the order of the observations. All right, would converting your height to centimeters change your z-score? Now, this is the one that you might not be as sure on, so let's just do the calculations and see. All right, so z equals, all right, my observation was my 66 inches, which when converted to centimeters was 165, minus a mean of 154.5 divided by 6.40. Now, again, we're rounding here, so let's just keep that in mind when we get our final answer here. So 165 minus 154.5 divided by 6.4 is 1.64. All right, so it did not change, which is what we should have expected. All right, and the reason we should have expected that is because we said from the beginning, z-scores are unitless. Right? They don't care what the unit is. So by changing from inches to centimeters, it doesn't change how far above or below the mean are because the z-score sort of strips away the units. Right? That's one of the advantages of it is that the z-score strips away the units so that we can compare things from different observations, different distributions, and have sort of an equal comparison. So again, z-scores don't change with the units. All right, now, what would a distribution of z-scores look like? All right, so what would a distribution of z-scores look like? Now, if we think about a z-score is really two transformations. Right? A z-score is two transformations. All right, transformation one is subtracting the mean. Transformation two is dividing by the standard deviation. Now, we're using words here, but this is basically subtracting a constant, and this is dividing by a constant. So let's just think about a little example here. Let's just pretend the mean of a distribution was, we'll say 10, and the standard deviation of a distribution was 2. All right, these are just made up numbers. If I were to convert every single observation into a z-score, that would mean that from every single observation, I subtracted the mean. All right, so if my starting mean was 10, and I subtracted 10 from every observation, my new mean would be 10 minus 10, or 0. So if you turn every observation into a z-score, the new mean will be 0. All right? Because again, if this was your starting mean, 10 minus 10, which is the rule we just learned, is 0. Now, the rule we learned for standard deviation is if you divide every observation by a constant, which is what we're doing in the z-score formula, you divide that measure of spread by the same constant. So if I divide 2 divided by 2, it's going to be 1. All right? So again, the mean will be 0. I'm going to, instead of having a period here, I'm going to cross that out. And the standard deviation will be 1. And this is going to be really useful to us down the road, because what this effectively says is that no matter what my starting distribution is, all right, if I turn everything into a z-score, I'm guaranteed that that new distribution of z-scores will have a mean of 0 and a standard deviation of 1. And again, this is going to be really helpful when we start looking at the normal curve. So just keep this in mind, that if we turn everything into a z-score, no matter what it was at the beginning, it doesn't matter what it was at the beginning, the mean will always be 0. The standard deviation will always be 1. And again, just think about the transformation. You're basically doing mean minus mean, which is always going to give you 0. And you're basically doing standard deviation divided by standard deviation, which is always going to give you 1. So it doesn't matter what you started off with, you're always going to end up with that result. Okay? So one last page, and then we're done for today. So this is actually kind of a preview of where we're headed. So it doesn't really deal with everything we just talked about. It's more of a preview of kind of where we're headed when we look at the normal distribution. So the normal distribution is this sort of bell curve that you've seen for who knows how many years at this point. But the normal distribution is just a special version of what we call a density curve. And a density curve is a curve that approximates a histogram showing the general shape of a distribution. All right, so for example, if this was our histogram, notice that the curve that we're drawing on top of it, and it's a little faded here, but we're not trying to recreate every single little up and down in the bars. We're just approximating kind of the general shape of the distribution. And that would be our density curve. And usually when we're drawing a density curve, we don't actually draw the bars underneath. We just say, oh, here's the shape of our distribution, and we represent that with a density curve. Now, some properties of the density curve. So if something's in a real density curve, a couple of things to know. It's always on or above the horizontal axis. So it should never be going below the horizontal axis. And this next one is probably the most important. It always has an area under the curve of exactly 1. All right, so the area under a density curve is exactly 1. All right, and that's going to be really important, because what we're going to soon learn is that the area that a curve occupies is going to translate to a percentage. All right, so if the area under a curve is always 1, sorry, not the area of any curve, but the area of a density curve is always 1, that 1 represents 100% of the possibilities. And then we can calculate percentages by seeing like, oh, well, if the whole curve is 1, what's the area of just this section? Now, we know it's going to have to be a number between 0 and 1. So maybe it's, 0.27, I'm just making that up, which would correspond to 27% of the curve, because again, the whole thing is always 1. So there's going to be a direct correlation between the area and the percentage of the curve that's being taken up. And then last but not least, and this was kind of part of the definition, but it shows the overall pattern of a distribution. All right, and we can use these in the same way that we were using our histograms earlier. So like if we have a density curve that's symmetric, we can say, oh, the mean and the median are approximately equal. If we have a density curve that's right skewed, we can say, oh, there's higher values up here that are dragging the mean to the right. So the mean is going to be a little higher than the median. Remember, the median is sort of the halfway point. And the mean, you can almost think of it as like the balancing point. So that's kind of what this says down here. The mean is the balancing point. Like if you're almost going to picture trying to balance this curve on your finger, it's where you'd have to put your finger so that it didn't wobble on or off. And then the median is the equal area part. So that means that 50% of the area is to the left of the median and 50% of the area is to the right of the median. Or put another way, the area to the left is 0.5 and the area to the right is 0.5 because, again, the total area is always equal to 1. All right. So, again, this is going to be stuff that is very relevant as we move into day 3 of this unit, where we start looking a little closer at the normal distribution. All right. So, again, I hope this was useful. If you have any questions, obviously reach out, and I will see you when I see you. Bye.